Hello everyone, this is Dr. Feng Tian from Governor State University. Today we will introduce a few important discrete probability distribution. In this section we will learn the statistic properties of binomial, Poisson, and hypergeometric distribution. We will also learn how to calculate the probability for a given binomial and a Poisson distribution. Also we will talk about the characteristic of each of these distributions and how to use these distributions to solve business problems. So first, let's take a look at the binomial distribution. Binomial distribution is one of the most important discrete probability distribution. And the reason it is important is because in reality, a lot of the events follows binomial distribution. Here we list just a few examples. For example, if you are working in a manufacturing plant and you're doing the quality control, you try to identify, well, among a certain batch of the output, what is the probability that you get a certain amount of defects? Well, this number of defects within a given output batch follows a binomial distribution. Or you're trying to do a field study and you do some survey. And you go out and send out some survey questions and collect some result from the respondent. Now, you take a look at the result and try to identify for a given question what is the probability that a certain percentage or certain portion of the respondent agree or disagree with your question. This result follows binomial distribution as well. We take a look at all these examples and try to identify the common property of these variables, and these are the requirement or the condition a certain variable satisfies binomial distribution. The first one is there is always a fixed number of observations. For example, if we're trying to study the number of heads we can get from a certain number of toes of coin, then the number of toes of a coin is a fixed number of observations. Or if we are trying to do the quality control and we examine the defect rate for a given output batch, then the number of items in this given output batch is the fixed number of observations. Or take a look at the previous example about the survey result. Then the number of the respondents we collected is the fixed number of observations. So for binomial distribution, first we have a fixed number of observations, and usually it is denoted as n. Second, each observation or each outcome from the observation is categorized as to whether or not the event of interest occurred. Well, in the example of tossing a coin, then the output of the coin will be either head or tail. Clearly, there are only two events. If we take a look at the quality control example, after we examined the output, we should label it either to defective or not defective. These are the two categories. Now the question is it true that the binomial distribution can only be applied if the outcome from the observation have only two events? Well, the answer is yes and no. The answer is yes is, well, you should always see the outcome should be categorized to two categories. One category is the event we're interested in, and the other category is the event we're not interested in. So this is true. We should always be able to categorize the output into two categories. But the answer is no, is the real output from the experiment may have more than two events. For example, I'm trying to study the probability that we get a certain number of 6 when we roll a dice. Well, assuming that I roll the dice 5 times and I try to understand what is the probability that I get at least 3 6 in these 5 experiments. Now here we all know that the output from rolling a dice actually has 6 outcomes. 1, 2, 3, 4, 5, 6. Does it mean this probability is not a binomial distribution? The answer is no. Well, it is true that there are 6 outcomes from rolling a dice. However, here what I care or what I interest is just the number of 6 within the experiment. Now when I look at this, I can always classify or categorize the output from rolling a dice into 2 categories. The first category is, well, 6. This is the one that I'm interested in. I'm trying to study. The second category actually includes the rest, or we can call it non-6. It includes 1, 2, 3, 4, 5. By doing so, I classify all the outputs into 2 categories. The category I'm interested in and the category include all events I'm not interested in. So the probability distribution is still a binomial distribution. And not only there are only 2 categories in the binomial distribution, these 2 categories are mutually exclusive and collectively exhaustive. Mutually exclusive means the 2 categories cannot occur at the same time. It will be either one or the other one. Like we toss the dice, it should be either tail or head. You cannot get both of them at the same time. And also, these 2 categories should be collectively exhaustive, which means, well, it includes all outputs, just like the example of rolling dice. All output 1, 2, 3, 4, 5, 6 are classified into 2 categories. 6 belongs to the category that we are interested in, and all the other 5 are in the category of event we are not interested in. So they are mutually exclusive and collectively exhaustive. Now because they are mutually exclusive and collectively exhaustive, when the probability of the event of interest is presented as pi, then the probability of the event of interest not occurring will be 1 minus pi. So we can always use pi and 1 minus pi to represent the probability that the event of interest occur and the event of interest not occur. The third requirement is the probability for the event of interest occurring for each observation should be constant, which means the probability for the event of interest occurring should be the same for each observation. Just like when we toss a coin, every time, it doesn't matter how many times we toss a coin, the probability we get a head is always 50%. Same in the rolling dice example. It doesn't matter how many times we roll the dice, every time the probability we receive a 6 is 1 out of 6. The last one is observations are independent. So if you remember, the definition of statistical independence is the occurrence of one event does not affect the probability of the occurrence of another event. So here the observations are independent means the outcome of one observation does not affect the outcome of the other one. Which means I tossed a dice and got a head. And this head, or the outcome from the first time I tossed the dice, will not affect the outcome from tossing a dice when I do it one more time. So this is the requirement of observation are independent. Now in reality, most of the time the problem is not as simple as we toss a dice or we toss a coin or roll a dice. So how can I identify whether or not these 2 conditions are satisfied? Usually, if one of the following 2 conditions is satisfied, then we can assume that these two requirements are satisfied. The first is if we are sampling from an infinity population. So if the population size is large enough, or we can consider it as infinity, then we assume that each individual sample will be independent from each other. Or if the population size is limited, we have a finite population, but every time after we perform an experiment or we draw a sample, the sample drawn from the population will be replaced. The replaced can be that we put back the sample we draw, or we have some substitute that can be refilled into the finite population. If either one of these two conditions is satisfied, then we can consider the two requirements for the binomial distribution are satisfied. Once we know a certain probability distribution is binomial distribution, we can use this formula to calculate the probability. Here, if we take a look at the formula, we have basically three variables or three notations here. One is n. N is the sample size, or the number of observations we have. And pi is a constant. Is a variable, or the probability of event of interest. And the third one is x. X is the number of event of interest in sample. So if we have these three numbers, then we can use this formula to calculate the probability. Now let's take a look at an example and see how this probability, the binomial distribution probability, is calculated. Now, the example said it is known that Jim has a probability of 10% or 0.1 to hit a home run every time. What is the probability that Jim can hit one home run in 5 tries? Now remember, the three parameters we need to calculate the binomial distribution are n, the number of observations or number of sample size, pi, the probability that in each observation the event of interest will occur, and then x, which is the probability we're looking for. Now in this example, it said first, Jim has a probability of 0.1 to hit a home run every time. So the question asks us the probability of hit home run. So hitting a home run will be the event of interest. Now the probability that this event will occur is 0.1, so the pi is 0.1. Then the question asks us, what is the probability that Jim can hit one home run in 5 tries? Which means the sample size or number of observations is 5, so we have n equals to 5. The last one is, we're looking at among these numbers of observations, or in this sample size, well, we are only interested in, well, one of these observations had the event of interest, or the event of interest only occurs in one of these 5 observations. Now, remember, it is not as simple as 1 out of 5, or it is not as simple as 1 out of 5 times 0.1. The reason is, well, we are only looking at one home run in 5 tries, but this one home run can happen in the first try, second try, third try, fourth try, or the 5th try. It can happen in either one of them. So the probability should consider all these 5 conditions, or all these 5 possibilities. So that is why we need to substitute all these numbers into the formula to do the calculation. Now, the formula is probability x equals to 1. So this is that the number of events will occur only once within a given number of samples or given number of observations. And we have n equals to 5, x equals to 1, and pi equals to 0.1. We substitute all these 3 numbers into the formula, and eventually we got a probability of 0.32805. Well, if you think it's just 1 out of 5 times 1, well, then that will only be 0.02. It's much, much smaller, see? So the probability is different. Now let's take a look at another example. Suppose the probability of a computer to have a problem within its warranty is 0.02. What is the probability that at least 2 computers have problem within warranty in a group of 10? Now here the probability of a computer to have problem within its warranty is 0.02, and we are looking at the probability that a certain number of computers will have problem within warranty. So the event of interest is having problem within warranty, and the probability for each one of them, for each individual computer, is 0.02. So we have pi equals to 2. Second is we're looking at a group of 10, or the sample size, or the number of observations is 10. So we have n equals to 10. But what is different from the previous example is this time I'm not looking at the probability that exactly 2 computers will have problem within warranty in a group of 10. I'm looking at least 2 computers, which means, well, I'm looking at the probability, and this probability includes 2 computers have problem within warranty, 3 computers have problem within warranty, and all the way up to what? All the way up to 10. All 10 computers have problem within warranty in a group of 10. Now, how to do the calculation? Of course, the straightforward one is I can calculate that the probability that 2 computers have probability within warranty, and the probability 3 computers will have problem within warranty, and the probability that 4 computers have problem within warranty, and all the way up to 10 computers. All 10 computers have problems within warranty. And then I can add up all these 9 numbers. That will give me the answer, because this answer will give me at least 2 computers. At least 2 computers have problem within warranty. However, there is an easier way to do the calculation, which is, remember, for any probability distribution, the probability that all event occurs add up will always be 1. Now, for this problem, we have only sample size of 10. And if we look at the event we are interested in, the number of events we are interested in can only be from 0 to 10. So 0, 1, 2, 3, 4, all the way up to 10, which represent the number of computers have problem within warranty in a group of 10. Now, which means the probability that no computer have problem within warranty, plus the probability that only 1 computer have problem within warranty, plus the probability that 2 computers have probability within warranty, and all the way up to all 10 computers have problem within warranty. These 11 probabilities add up should be 1. Now I'm looking at the summation of probability 2 up to 10. Then we can actually do the calculation. We can easily calculate the probability that non-computer have problem within warranty, and we can calculate the probability that only 1 computer have problem within warranty. And these 2 probability add up with the probability that at least 2 computers have problem within warranty. This should add up to 1. So if we use 1 minus these 2 probability, that will give us the probability at least 2 computers have problem within warranty. So in the binomial distribution probability problem, you should always be careful to what the question asks. Does the question ask us the probability that exactly a certain amount of event of interest occur within the observation, or it asks at least a certain number, or it asks us no more than. So for the latter two, usually it includes more than one probability. You need to be careful. So for binomial distribution, the characteristics are n and pi. N is the number of the observation, and pi is the probability that the event of interest will occur in a given observation. So with these two numbers, we can easily calculate the mean and the variance and the standard deviation of the binomial distribution. And actually, all these three characteristics can be calculated through the two numbers, number of observation n and the probability of event of interest occur, pi. Next, we'll look at the Poisson distribution. Poisson distribution is about similar stuff as binomial distribution. It is about the case that we are interested in the number of times an event occurs. But however, the difference between Poisson distribution and the binomial distribution is, if you recall, in binomial distribution, we are looking for the number of event of interest that will occur with a given number of observations. But here, the Poisson distribution is used when we are interested in the number of times an event occurs in a given area of opportunity. So this is the major difference. What is area of opportunity? So area of opportunity is a continuous unit or interval of time, volume, or such area in which more than one occurrence of an event can occur. Now here are some examples of Poisson distribution. For example, the number of scratches in a car's paint, the number of mosquito bites on a person, the number of computer crashes in a day, and the number of car accidents over a certain range of road. Now we see the difference between the binomial distribution and the Poisson distribution. In the binomial distribution, the number of events of interest, it is within a certain number of observations or certain number of samples, and the output from this sample can be classified into, well, event of interest and not event of interest. Now here, for the Poisson distribution, the area of opportunity usually is a totally different measurement. It's totally different measurement from the number from the event occurs. For example, well, the number of scratches in a car's paint. The area of opportunity is the whole area of car's paint, but the event we are looking for is the number of scratch. The number of scratch is in a totally different measurement from a car's paint. The second example, well, the number of mosquito bites on a person. The measurement of the area of opportunity is a person's body, and the event we are looking for is a mosquito bite. Now, this is the first difference. In the binomial distribution, basically, the number of observations generate the event of interest. But here in Poisson distribution, the area of opportunity is usually different measurement from the event occur. Second is, in the Poisson distribution, the number of observations n actually put an upper limit of the number of event of interest can occur. For example, when you toss a coin 3 times, you cannot get more than 3 heads from this experiment. The number of experiments, 3 tossing, actually limit the number of event of interest we can get, number of heads we can get. However, in Poisson distribution, because the area of opportunity is in a totally different measurement from the event occur. So there is no, at least theoretically, there is no upper limit of this number of times an event can occur. For example, the number of scratches in a car paint. Well, it can be 0, 1, 2, 3, 4, 3, 5, 6, 7, all the way up. It can be 1,000, 2,000, or theoretically it can go to infinity. Well, the number of computer crashes in a day, theoretically it can be unlimited as well. So this is the second difference from the Poisson distribution to the binomial distribution. So when you try to distinguish, or when you try to make the judgment whether or not a given distribution is Poisson distribution or a binomial distribution, these are the two things you need to consider. When should we use Poisson distribution? Here give us a few applications. We can use Poisson distribution if we want to count the number of times an event occurs in a given area of opportunity, or when the probability that an event occurs in one area of opportunity is the same for all areas of opportunity, and the number of events that occur in one area of opportunity is independent of the number of events that occur in the other area of opportunity. And the last one is the probability that two or more events occur in an area of opportunity approaches 0 as the area of opportunity becomes smaller. So similar to the binomial distribution. Binomial distribution, if you remember, there are 4 conditions or 4 requirements. And here, these 4 requirements are the requirement to judge whether or not a given distribution is a Poisson distribution. Now, how to calculate the Poisson distribution probability? This is the formula. Again, we have 3 parameters in this formula, but not like the binomial distribution. Poisson distribution, these 3 parameters, one of the parameters is actually the constant, which is the E. E is the base of the natural logarithm system. It always equals to 2.71828. So basically we only have 2 parameters. One is lambda, which is the expected number of events for a given unit of the area of measurement. And the other one is x, which is the number of events in an area of opportunity. Now let's take a look at the Poisson distribution characteristics. Well, the unique part for the Poisson distribution is the mean and the variance always equal to the expected number of events in a given area of interest, area of opportunity, which means the mean and the variance always equals to the lambda. And of course, the standard deviation is the square root of the variance, so it's square root of lambda. An example, the number of work-related injuries per month in a manufacturing plant is known to follow a Poisson distribution with a mean of 2.5 injuries a month. Now the first question asks us, what is the probability that in a given month no work-related injury occur? Now first we have the average occurrence equals to 2.5 injury. And now we are looking at the probability that x, which is the number of events occur, equals to 0. We substitute the 2 numbers into the formula and get a probability of 0.0821. So which means given that a Poisson distribution with a mean of 2.5 injury a month, then the probability that no work-related injury occur in a given month is just 0.0821. Well, similarly, we can calculate what is the probability that in a given month at least one work-related injury occurs. Now again, we have at least one. It means it includes the scenario that one injury occurs, two injuries occur, 3, 4, 5, 6, all the way up to, well, theoretically infinity. And again, we can use 1 minus the probability that non-work-related injury occur to calculate this probability. So we use 1 minus 0.0821 we calculated earlier to get the probability that in a given month at least one work-related injury occur is 0.9179. The last probability we introduced today is the hypergeometric distribution. The hypergeometric distribution is similar to binomial distribution. The only difference is, remember, previously we mentioned that in binomial distribution there are requirements include that, well, the probability that the event of interest occur is constant. And second is the outcome from the observations are independent from each other. Well, in the hypergeometric distribution, these two requirements do not satisfy anymore. If we try to summarize the difference, the binomial distribution is applicable when selecting from a finite population with replacement or from a finite population without replacement, where the independence of the observation outcome and the constants of the probability of event of interest are satisfied. While the hypergeometric distribution is used when we are selecting from a finite population without replacement. And this without replacement makes the finite population, with the finite population actually makes the outcome from the experiment or observations do not independent from each other anymore. So it is similar to binomial distribution. The only difference is that the outcome from trial are dependent. So it is concerned with finding the probability of X items of interest in the sample where there are A items of interest in the population.